Our next speaker is Michael Perlmutter, and he's going to talk about geometric wavelet scattering networks on compact Riemannian manifolds.
Hello, everybody. It's a pleasure to be able to talk to you all today. I'm also going to be talking about the scattering transform, which was a central topic of a very excellent talk this morning by Stefan Mallat. But I'm going to be talking about a new variation, which is for data with geometric structure. And this is a joint work with Guy Wolf of Montreal, Matt Hearn, who has been my mentor at Michigan State for the last several years, and also Feng Gao of Yale. So for anyone who wasn't here this morning, the scattering transform is a mathematical model of convolutional neural networks which uses pre-designed wavelet filters. And one of the motivations for this is that we have filters where we know exactly what the filters in the network are, and so we're able to study them and analyze them with rigorous mathematics, and we're able to provably show that it has desirable properties such as invariance or stability. In addition to being a useful theoretical tool, the scattering transform is also very numerically effective, and it also can operate in limited training data environments because it doesn't need to learn the filters from training data. So, formally speaking, what the scattering transform does is it inputs a signal f and outputs a series of coefficients, where at each layer, the input signal f is first subject to a linear transformation, which is convolution against a wavelet filter, and then a pointwise nonlinearity, which is either the complex modulus or the rectified linear unit. And then given this one layer, it does one of two things. It outputs an invariant measurement, which can be done either by taking the L1 norm or convolving it at a low-pass filter at a scale 2 to the j. And then you also keep going, and you apply another wavelet transformation and another nonlinearity, and then you output an invariant measurement again. And in this way, this models the feed-forward layers of a CNN, with the primary difference, in addition to the wavelet filters, being that you're outputting measurements at each layer. But overall, this largely has the similar structure to a CNN, with an iterative cascade of wavelet convolutions and nonlinearities. And some advantages where it's really useful can be if you want to incorporate underlying physics of the problem at hand. So in an example of this, some of the other people in my research lab at Michigan State have been studying a project on quantum chemistry where they're trying to model the formation energy of lithium silicon molecules. And what they do is they use wavelets, which are modeled after the solution to the Schrodinger equation, which is known to be a good physical model for the problem. Kind of a fun example, which was done by Yang Wang and some other people, is art authentication, where they have a data set of about 80 paintings. 60 of them are Van Goghs and 20 of them are forgeries. And this isn't enough training data to be able to train a CNN on it because there's only 80 of them. Even if you had a bigger data set, it's not like Van Gogh painted 1 million paintings. However, you're able to use scattering and still get 97% accuracy for determining if it's a real painting or a fake one. So the focus of our talk is going to be a new variation of the scattering transform, which is for data with geometric structure. This is part of the new field of geometric deep learning, which aims to take the success of CNNs and translate it to other data types, either graphs or manifolds. And today we're going to be mostly focusing on manifolds, although similar constructions have also been done for graph structured data. And the key is that we're going to define wavelet convolutions using the spectral decomposition of the Laplace-Beltrami operator. And then given that, we can then build the scattering transform as a multi-layer wavelet network, and then apply it to some geometric deep learning tasks. So from a technical standpoint, the key difference in the construction is how you build the wavelet filters. And before I give the details of that, I'm going to give some examples of some typical tasks we might apply this to. The first big family of tasks is when you have one known manifold, which for us we're going to take to be the sphere in this picture, and then you have a bunch of different signals which are all labeled on this manifold. And for our signals, we took the MNIST data set and we projected it onto the sphere. And then we did the geometric version of the classic MNIST classification problem, where we had our network determine what digit was what, and are able to get 95% accuracy on the spherical variation of the MNIST problem. The second big class of problems is telling apart different manifolds. And for this example, what we did is we took the Faust data set, where we have 10 different people standing in 10 different postures, so it's a total of 100 different manifolds. And again, this is a small data set, so the fact that we're using pre-designed wavelet filters is very useful. And we're able to tell which person is which with 81% accuracy, and also what pose a given person was standing in with 95% accuracy. So in order to do this, you need to have some meaningful way of defining the same signals on different manifolds, because then what you can do is you can compute the scattering coefficients of the same signal on different manifolds, take the L1 norms and get a list of numbers, and if the manifolds are similar, the scattering coefficients should be similar, and then we can feed this into a support vector machine. And so what we did is we used shot descriptors, which are these generic signals that can be defined on 2D surfaces that were developed by Tambari and Prakya. So those are the kind of examples of the sort of tasks we're interested in. So now I'm going to give some more details on how we actually define the wavelet transform on manifolds. And the key is the spectral decomposition of the Laplace-Beltrami operator. So we're going to let phi k be an orthonormal basis of eigenvectors. And then given an arbitrary function in L2, we can expand the function in this basis, and we think of this as a generalized Fourier series. Then, given a filter H, we can consider an operator which convolves the signal f with the filter H as a pointwise multiplication of Fourier series operators. So this is a direct generalization of the well-known fact that convolution is Fourier multiplication in the Euclidean setting. Now, a difference is that in an arbitrary manifold, these eigenvalues can have crazy multiplicities. So if we happen to have an eigenvalue with multiplicity and lambda k is equal to lambda L, we're going to require that the kth and the lth Fourier coefficient of H be the same. And this is what we call a spectral filter. And the reason we need spectral filters is because this leads to an equivariant network. This is a theorem by picture, where we say that if we have a spectral filter, we input a signal and we filter it, and then we rotate it. This is the same as we first rotate it and then filter it. This is a direct generalization of the fact that translations commutes with isometries in the Euclidean setting, but here we need to make this additional assumption on spectral filters because the isometry group on an arbitrary manifold can be a lot more complicated. But even in the Euclidean setting, arbitrary convolution is not going to commute with rotations, so this really is a very natural condition to impose. Now, given this, we need to now construct a wavelet filter bank, and we want to be able to have the same wavelets on different manifolds. So what we do is we start with a spectral function g, which is just a function on the real line and is independent of the manifold. In a typical example, we choose g lambda to be e to the minus lambda. And we define a low-pass filter by evaluating g at the eigenvalues dilated to a scale 2 to the j. And then we construct wavelets by evaluating this low-pass at different scales, squaring them, and subtracting them. And this is meant to parallelize constructions which have been used in the graph setting by either Koifman and Maggioni or by Shannon, based on the heat semigroup, which coincides with our low-pass filter in the prototypical case for g lambda is e to the minus lambda. So that was a bit of a technical slide. So as a pictorial illustration of our wavelets, what we can see is at the far left of the screen, we have very localized wavelets. And then as j increases, as we move across the screen, the wavelets get more and more spread out. And so these wavelet filters at different values of j are looking at the manifold at different scales, where here the measurements are very localized, and here they're more globalized. We can also analyze this network theoretically, And essentially, the one sentence summary of this slide is we prove all the same theorems about the manifold scattering transform that Stefan proved about the original scattering transform. To be more specific, what we do is we see that if we have Lipschitz continuity with respect to the input signal, meaning if we take a function f1 and replace it with a new function f2, the scattering transform will change by no more than the change in the original function. So this is a continuity. We also care a lot about invariance. So say we have zeta as an isometry on the manifold, and we precompose f with an isometry, and then we take the scattering representation of this isometric perturbation of f, and we compare that to the scattering representation of the original signal. These will differ at most by a factor which depends on the scale of the low-pass filter. So for full manifold classification tests, we take j to go to infinity, and in the limit we have that the scattering transform is going to be isometry invariant. Lastly, we also want the notion of stability. So here, rather than composing a function with an isometry, we're going to compose it with a diffeomorphism, and the amount of representation will change will depend on the scale of the low-pass filter, and also a quantity which depends on how far away the filter is from being an isometry. And the last thing I'll say before I wrap up is that similar results are all provable for the graph counterpart, the graph scattering transform. So in summary, the scattering transform is a wavelet-based model of CNNs that works well in limited labeled and data environments and can be designed to incorporate physical understanding. And we introduced a manifold version, applied it to a variety of geometric deep learning tasks, and also showed that it has theoretical properties which are similar to its Euclidean predecessor. And that is where I'm going to stop, so thank you very much for listening to my talk.
Very interesting talk. Can you comment on the slide where the manifold is the sphere? And you talk about spectral filters. I was trying to understand the requirements you had. Would this work if you know already that the basis is spherical harmonic basis and then you do some sort of filter on that basis or not?
So yeah, actually, yeah. So in the special case where it's the sphere, then the assumption of spectral filters, you can kind of get around that. And actually, that's something that's done in the quantum chemistry project done by the other people in my lab that I alluded to briefly, where they use steerable wavelets, which are expanded into spherical harmonics. And what they do is then they're able to restore rotation invariance even without spectral filters by using a special activation function, which pools together the wavelet transforms that correspond to the same basic frequency.
Thank you. We have one more question. Could you give just a couple more details on how the manifold is specified in the algorithm? So does the algorithm work if the manifold is just represented by a point cloud?
Oh, if the manifold is just represented by a point cloud?
Yeah.
Okay, so yeah, this gets to a couple of things, which is in order to implement this, we do have to discretize our manifold and implement a data-driven graph where we have to use a discretization of the Laplace-Beltrami operator. Something which is related to this question is that the discretization of the Laplace-Beltrami operator is going to be fundamentally different than the graph Laplacian. But if we just had access to a point cloud, what we'd have to do is we'd have to do some sort of manifold learning algorithm to implicitly learn the Laplace-Beltrami operator. And then we would have to say we'd have to know the function at the point cloud and hope that we can interpolate that to the full thing and somehow do we would use our approximation of the Laplace-Beltrami operator and then also some approximation of the function from the mesh points in order to implement it.
Thank you very much.